dimension should be of nanometer size. So what happens actually? Now nanoparticles, how it happens, and clustering of atoms and molecules are in the range of 1 to 100 nanometer. So basically, if you take the scale and we normally consider the nanoscience, the nanotechnology, okay, like within the range of 1 nanometer to the 100 nanometer. So means your size should be within this range. If you are dealing with this size range of the particles, then you can say, yes, this is uh, my research into the nanotechnology. Now, what are the advantages? Advantages is superior surface to volume ratio, then excellent surface morphology. Now, for understanding, now how we will like compare nanoparticles. Human hair is 5 orders of magnitude larger than nanomaterials. Normally, okay, like human hair is 5 times. So you can okay imagine what is the size of nanoparticles. So what actually you dealing actually? So we are dealing with nanoparticles, that is one of its dimension in nanometer or 10 to the power minus 9 meter. So what you are expecting? Expectation is a new era of technology utilizing intensively small things, leading to the extraordinary behavior in the properties of the materials. So that is our expectations, and that is what okay people are reporting actually. So now there is okay so much of research being reported by several researchers actually, and there are even the simulation. Now this picture you are seeing is a simulated picture actually. A simulated picture, we will come back here actually, but let us try to understand what it does actually. Ability to control or manipulate materials at the atomic scale, which normally micron size particles is unable to do actually. To control or manipulate in the atomic scale. Now it improves the bulk properties, mechanical properties, durability, sustainability, and volume stability. Also, the lower level of environmental contamination. How it is happening? Now let us see this picture actually given by Thomas et al. 2009. Now you can see here these are C3S cement particles. C3S cement particles, and you can see here like once the water is added and the hydration process started, and see here after the complete hydration how the hydration products is nothing but is red color actually, red color. The grays color is the gray color is the cement grains, that is unreacted cement particles, and the white color is nothing but your porosity actually, the pores. So now same actually calcium like C3S cement grains, let us add some nanoparticles. So you can see the small dots is nothing but your nanoparticles, a very okay less quantity of nanoparticles were added to the cement. Now you can see how okay these nanoparticles are making the hydrogen products or hydrogen reaction into a very advanced stage. You can see here in the right side picture how okay the entire area is covered with the hydration products, that is calcium silicate hydrate, leaving very less space for the pores as compared to the previous picture. So what happens actually here? Now nanoparticle, the moment you add it, it itself started acting as a calcium silicate hydrate seed. So itself, because into the nanometer scale itself is taking as a calcium silicate hydrate seed, and that is the way it promoted the hydration reactions. So that is a beautiful simulation okay done by the Thomas et al. In 2009. Okay, so regarding the nano SiO2, now when we say about the nanoparticles, particularly for the civil engineering materials, we know silica based materials are very good for us actually. So there are so many varieties of nanoparticles. There is nano SiO2, nano Al2O3, nano Fu2O3, nano TiO2. There are many, okay, there are many such products are available in the market, and research also are being done on so many varieties of nanoparticles. But nano SiO2 is being widely applied, particularly in the cement-based materials. So first nano product that replaced the microsilica or silica fume is the nano SiO2. The nano SiO2 composed of silicon dioxide as the chief chemical constituent. Particle size can be varied, okay, 5 to 658 nanometer actually. from the literature review or the research reported by the so many researchers, we realized some people have used even to be able to handle 5 nanometer, but some people are okay, like even has gone up to 658 nanometer with spherical morphology. Now, this is a beautiful, okay, actually flow chart is given, okay, by the influence of nano SiO2 on the concrete properties. Now, small spherical particles in nanosilica, like there are two ways it improves the engineering properties of concrete. One is fill in voids, another is highly pozzolanic. Now let us see how it fills the voids. Now dense packing, actually, dense packing expels all the water. Means, okay, let us go one by one. Now when it fills the voids, because very small size particles, it is trying to fill the pores. So that way we get dense packing. And the moment we get dense packing, our porosity becomes very less. And less porosity, we know it improves the durability properties. Now here, now expels water. Now more water available for the molding and improve plasticity. Now sometimes we have seen like nanoparticles consume, okay, little more water, all right, but I am talking about the chemical bound water. The chemical bound water normally, okay, it expels, and that helps in the molding and improves the plasticity. Then regarding the pozzolanic behavior, so how it works actually, it consumes lime from cement reaction. What is a lime actually? Lime is nothing but your calcium hydroxide, that is unwanted hydration products. So once it consumes lime from the cement reaction, then improves early as well as final strength. So that is the advantage for us. Okay, the moment you use nanoparticles, the early strength development is very, very good actually, as well as the final strength. Then improves possibility for nanofiller use. So that is the way it improves the properties of the concrete or cementitious composite. Okay. Then there are some weakness. See, every like advancement will have a negative actually. So similarly, the nanoparticles also have some kind of weakness. Now, what are the weakness? See, induces drying shrinkage, because as I was telling you, in the casting stage, it consumes more and more water actually, and then autogenous shrinkage, thereby developing a large number of cracks in concrete. So that is very, very important actually. The moment you need to use nanoparticles, you have to understand, like, we have to control the shrinkage. Then at this point of time, till now we have seen it is very costly actually. It is a non-economical product. Then high heat of hydration, because it advances the hydration reaction. So heat generation is very high and ultimately resulting into the slump loss. Well, nowadays slump we can manage, okay, with the some kind of adding super plasticizer, but there are, okay, definitely some weaknesses. So what we realized actually, what to be done at this point of time, use secondary cementitious materials in conjunction with nanosilica. Possibly you can produce a high performance and sustainable concrete, and that's what is happened actually. So we realized it is difficult to eliminate the secondary cementitious materials. We know most of the secondary cementitious materials are available free of cost. Hardly, okay, we are being charged for the transportation cost. And we know nowadays we are replacing the cement, secondary cementous materials up to 20-25%. It has become a common practice actually. So it is difficult to completely eliminate the secondary cementous materials. So rather than you go for addition of very small percentage of nanoparticles with the suitable amount of secondary cementary materials, and that help me in producing a high performance and sustainable concrete. I will talk about okay this actually. So what we have done actually for going for okay this job, we have proportioned the mixture into different different proportions, that is binary, ternary, and the quaternary blended. Now selection of right combination of materials playing a vital role. Now thorough knowledge and understanding of the raw materials and the basic properties is very much essential. Then choosing suitable combinations of replacement material by adopting trial and error technique becomes a tedious job. So what we realized, what should be the proportion actually of nanoparticles? That is going to give me an ideal proportion. And what should be the proportion of secondary cementitious materials? So we have tried so many combinations, but we have realized this trial and error found to be a tedious job actually. So what we did actually to overcome this difficulty, we have adapted the particle packing density. So we know actually what is a particle packing density. The knowledge of particle packing concept and its influence in this composite necessary to enable a mixture designer to select the right proportion of replacement materials from a pool of secondary cementous materials. So I will speak about it. Now we know what is a particle packing of concrete, nothing but is the packing density. So in soil mechanics, you must have studied the packing density is the volume of solids divided by total volume, that is Vs by Vs plus Bv. So by taking this concept, now you can see here what is the benefit we are going to get. Well, now assume this was my the mixture proportion. So in this picture I added some kind of small size fractions so that the pores get minimized. Again, in the last picture, still smaller particles were filled, and that helped me still minimize the pores. Now, what is the concept actually? So the void space between the large particles should be filled by the smaller particles, and the void space between these smaller particles is to be filled by further smaller particles, and so on. So if you do so, by which a minimized porosity or increased packing density can be obtained. So that is the actual objective of particle packing model or the particle packing density. Now how we will do it actually? Well, there are so many particle packing models are available in the literature. We realized there is a particle packing model given by modified Anderson and Anderson model. Is found to be one of the appropriate and best known packing models. So we have adopted this model for designing the mixture proportion of our material. So this is the formula actually, and these are the the corresponding terminology. So for doing this, you need to understand your raw materials. So that is very important actually. So optimistic properties like improving the hydration, compressive strength, filler effect, and dense microstructure of it aids for better durability of the material. So if you do so, ultimately it will help you in the improving the durability of the structure of the material. So, so idea is why we have adopted actually the particle packing concept, because the utilization of SCMs in conjunction with nanosilica as a binary, ternary, and quaternary blends in cement composite is very much essential to counterbalance the effects of secondary cementitious materials and nanosilica and to obtain high performance sustainable cementitious composites. Now we know there are some advantages of using secondary cementitious materials. Also, there are some disadvantages. And similar way, there are some advantages of using nanosilica. Also, there are some disadvantages. So what we have done actually in this research, we have combined, okay, both these materials, both these materials we have combined, but judiciously we have combined by adapting particle packing density so that both the negativity of these materials can be minimized and we will obtain a high performance sustainable cementitious composite. So that was the objective actually. So let us go into the experimental methodology. Now this is the physical properties of OPC, fine aggregate, okay, and the coarse aggregate, sorry, and the pliers and ultra fine pliers. Now all these, okay, these are our physical properties. This is okay, you can determine in your labs. And here is the physical properties of the nanosilica. Now nanosilica actually we have purchased from one of the lab in Mumbai. It is very costly actually, as I was telling you. And you can see here, this is the my particles distribution of all the materials. The colored nanosilica, ultrafine fly ash, ordinary Portland cement, fly ash, and sand. So let me like expand, okay, this picture actually. So you can see here now the x-axis representing the particle size and y-axis representing the percentage finer. Now close look into the particle size. Now this one is representing the sand, which is in the millimeter scale actually, millimeter scale. Now this is my nanosilica. You can see here, nanosilica is 0.01 to 0.1 micrometer. So that is nothing but your nanoparticles. And we have also used the ultra fine fly, as you can see here, particle size is almost 1 micrometer, is very okay, uniform size particles. And then this is my OPC and this is my pliers. So the variation is, so from millimeter to the nanometer is the particle size distribution of the materials. Okay, now how, okay, we have adapted actually the particle packing is nothing but the modified Anderson and Anderson model. As I was telling you, by adapting this, we have proportion the binary, ternary, and quaternary blend. So for this presentation, I have just restricted, okay, the presentation till only ternary blends. So you can see here there is a control that is only OPC. Then the binary blend, that is OPC plus fly ash plus OPC plus ultrafine fly ash, and the ternary blend consisting of all the three particles, that is OPC, fly ash plus ultrafine fly ash. So that is the way. And here the percentage replacements. All right, percentage replacements. So for doing this, there is a software called EMA. So this software helps me in like designing the mixes by adapting modified Anderson and Anderson model. And by, so first I determined what is the percentage found to be the best for the ultimate particle packing. So we have realized, like this is the, like for example, OPC plus ultrafine fly ash nanosilica, we have got 25% total replacement. We wanted to go for only 25%. So out of 25, 23 plus 2 gives me the best, okay, packing density. So that's why I've adapted 23% of ultrafine fly ash and 2% of nanosilica. Okay, and this table is nothing but your calculations. Just, okay, it is how much kg per meter cube of mortar is required. And we have fixed, okay, the binder to sand ratio of 1:3 and water point ratio we have adapted is 0.5. So that is the way, by doing so, we can determine the quantity per meter cube of the mortar. All right. Then we have actually two phases the casting was done. One is preparation of the blended motor specimens. Now, this was done with a automatic motor mixer. That is, the blending was done with a automatic motor mixer. Then the size we know that is for a motor 70.6 to 70.6. That is a cubical mold actually. So compressive strength and porosity was done with the help of these specimens. Then cylindrical specimens we have done, that is 100 mm dia and 50 mm height for the rapid chloride ion penetration test, that is RCPT test. So they were, after the casting, they were stored in humid condition and demolded after 24-hour storage. Once you demold after 24 hours, then you keep it for proper curing until the day of testing. That is normally here we have adopted a submerged water curing actually. Then testing methods for blender cement motor samples, that is test compressive strength, density, permeable porosity, and RCPT. And as per like standards, there are codes like we have adapted or some references. Then the remarks like compressive strength was done at the 3, 7, 20, 56 days. Same thing for density. Permeable porosity also same thing. RCPT was done at 7, 28, and 56 days. So you can see here, the pictorial representation. This is the motor mixer, which is an automatic motor mixer from the A mill. We purchased from A mill. Here the molds, cubical molds, and this is the mold for the rapid chloride ion penetration test. You can see here the samples, like with names, with different names. Then once they were demolded, then they were kept in the curing tanks, and it is all were submerged. Then this is the testing. This is the testing, like for the compressive strength, and this is the testing for the rapid chloride ion penetration test. Then also we have done the preparation of the blended paste specimens. Like for the paste specimens, also we have adapted the automatic motor mixer, but there is a different program actually. As for EN 1963, that was 1961 actually. Now what are the tests we have done actually? We have done the test setting time, surface temperature variation during the period of setting, workability, chemical shrinkage, and advanced characterization of hydrated paste samples. So you can see here, this is the mold actually. It is a typical actually chocolate mold actually. So the silicon mold, and the size we have, you can see here the size is mentioned here, and this mold was used for casting the samples for the advanced characterization studies. Okay, so it is the same like way the casting was done. Then only one thing what we have done actually, after the accomplishment of appropriate curing ages, samples were subject to solvent exchange technique using isopropyl alcohol for 24 hours. Because normally when you go for the advanced characterization studies, you don't get a slot on that day. Suppose 28-day testing is difficult to get a slot on 28 days. So we make ensure to stop the hydration actually. And there is a technique called solvent exchange technique, by help of which you can stop the hydration actually. And then wherever you get a slot, you go for the advanced characterization. That is, we done here the XRD, thermogravimetric analysis, and the SEM EDS analysis. So these are all the advanced characterization studies were done for the paste samples. I will explain you one by one actually. Then there are the testing methods for blended test specimens, cement test specimens actually samples, like setting time. This is the standard, and surface temperature. There is no standard actually, but we used the infrared thermometer. The workability, there is a standard, also some reference, that is through the mini flow table. Then chemical shrinkage through the ASTM standard, and you can see here these are the procedures or the picture representation how the setting time, surface temperature, just like a like surface temperature, the way like in the malls and all, they are measuring the same. This is the same equipment actually, is an infrared gun. Okay, and it measures the temperature, and you can see here the the mini flow table test measuring the workability, and the last is the your chemical shrinkage test apparatus as per the ASTM C1608. Then let us now go into the move into the methodology for the advanced characteristics. Now the most important part here is the hydration and microstructure characteristics. Now my topic, the delivery, try to understand is more into the hydration, okay, phenomena. How I am going to quantify the hydration products. That is most important actually. And we have done through the measurement of cement paste with the help of thermogravimetric analysis or thermogravimetric analyzer. So, so this is the standard, okay, like samples, okay, like are heated with a temperature range of 50 to 900 centigrade nitrogen per atmosphere at a heating rate of 10 degrees centigrade per minute. And this is the standard actually, purge rate of 20 millimeter per minute. That is a equipment, okay, requirements. Now, what happens actually? Now, there is lot of research scientists have done to determine how you are going to determine the calcium hydroxide content through the results of thermogravimetry. So there are, okay, there are equations. You can see here calcium hydroxide, it's converting to CO plus H2O, and and that is the way you can determine the CH, that is calcium hydroxide percentage, with this formula, and that is given by Singh et al. Then water associated to hydration products except the CH. Now remember, this is nothing but your calcium silicate hydrate. So because we cannot say it is exactly the calcium silicate hydrate, but it resembles to calcium silicate hydrate. And the weight loss, remember, happens between 35 to 600 centigrade. Here, calcium hydroxide between 400 to 500 centigrade. That is more important actually. So I will tell you the from the graphs how we determine, and this is the formula given by one of the researcher, and by adapting this, we can determine the water associated to hydration product except the calcium hydroxide. Then X-ray diffraction is being measured at 7 and 28 days. Now we know X-ray diffraction is for the mineralogical composition of the blended cement paste. So how determine? We determine to the intensity peak data obtained from the XRD, and you have to analyze through the expert high score plus software, right? Then scanning electron microscopy through energy dispersive X-ray spectroscopy. Now, how are we doing actually? We are doing through the image processing. Image processing will give me a morphological characteristics of the cementitious paste. But when you do EDX, that is energy dispersive X-ray spectroscopy, you can able to determine the change in elemental composition within the boundary of image. And that is going to help me in understanding in what level of or what degree of hydration has happened actually. So we'll see, okay, when the results and discussion. So yeah, come to the results and discussion actually. Then you can see here the first is the particle packing model by modified Andreessen and Anderson model. So all the pictures for all the mixes, whatever, okay, taken here, plotted in this picture. And most of the, like, you can see all the like fit, all the fit is close to zero 0.9. Okay, so you can see here the black one is the ideal curve, ideal curve. So remember, the more and more matching to the ideal curve is going to give you the best proportion of the mix, that will give you the best packing density. So here by using the software, okay, if you keep on, okay, doing this, then we did, okay, we realized this is the best, okay, packing density. But again we plotted actually, we try to realize or try to see how much okay it is close actually. So we understood okay they are statistically fit and all the curves fits well with the exponential relation. Exponential relation okay they are fitting very well to with the ideal curve. So we're sure yes what are the proportions that we have designed is absolutely fine actually. Now come to the compressive strength of the blended cement mortar. Now I have given okay the notifications that is for cement mortar, fly S 25, ultrafine fly S 25, that is fly S ultrafine fly S 25, then fly S nanosilica 25, and UNN means ultrafine fly S nanosilica 25. So that is the way is mixture is given actually. So now you can see here. Now you can see here, this the black one is the control actually, and and you can see here these are the fly ash mixes. Now what does it shows actually? The moment we replace the cement with the secondary cementitious materials, that is fly ash and ultrafine fly ash, and we know there is a problem of the early age, and here also we have obtained the same okay kind of behavior. All right. So improvement in strength noticed for fly ash and ultrafine fly ash mixes after 20 days only. So there was a lower compressive strength in the early ages, that is 3 days and 7 days. Now come to the ternary blended cement mortar. The moment you go for the ternary blended cement mortar, that is fly ash nanosilica 25 percentage, ultrafine fly ash nanosilica 20 percentage, you can see even the early age strength at 3 days increased by 10 percentage and 18 percentage respectively. Now that is the advantage actually. The moment you add, even though a very small percentage nursing, that is, you remember we have added only 2 percentage of nanoparticles and 23 percentage of secondary cementitious materials. Still, this very small percentage could able to increase the early age strength significantly actually. So what can be actually, what can be attribute to, so or due to nanosized silica particles promoted the early hydration reaction, and what is the phenomena nucleation site for the CSS calcium silicate hydrate. I showed you in one of the simulation picture by Thomas et al in the beginning, so maybe it helped us in a similar way. So nucleation site for the CSS gel formation and the pozzolanic reactivity. So that has helped in improving the early age strength for ternary blended mix, which contains the very small percentage of nanosilica, even though a significant increase obtained or increase of the compressive strength at the early age is obtained, okay, that we can see here. Similarly, the density and permeable porosity, this is okay, nothing but okay, your like just plots actually. Okay, density let us okay not discuss, but let us see the permeable porosity, because this is what is very important for us actually. Now you can see here that that is nanoparticles and ultrafine fly ash combination gives you the least porosity actually. Now here the porosity, the beginning in the initial stage was almost okay more than 25 percentage actually for a fly ash mix, fly ash 25 percentage. Now it is reduced to less than 15 percentage. So that is the beauty of the moment you add nanoparticles. And even in a later age strain, that is 56 day, it was almost okay 15 percentage, but reduced to close to okay 5 percentage. So that is the significant reduction okay of the permeable porosity. Remember, permeable porosity is nothing but is the porosity responsible for the permeability of the concrete. permeability of the concrete. And this size porosity is the more detrimental actually. Okay. So what is the like phenomena presence of multi-size mineral admixture along with cement particles have tailored the solidity of the mortar as well. Especially presence of nano-sized particles contributed in filling of the nanoscale voids, and that is the way it helped in reducing the permeable porosity. Okay. Similar way, the rapid chloride ion penetration test, that is RCPT, same phenomena actually. Now here the control is having the highest. Control is having the highest. The moment we add the secondary cementous materials and then the blended the with nanosilica, it started to keep on reducing the passage of charge, the charge passing through the cementitious composite. Now let us see the absolute values actually. Now percentage reduction in charge passed for fly ash 25, ultrafine 25, then fly ash, ultrafine fly ash nanosilica, and ultrafine nanosilica mixes at the curing at 56 days found to be 27 percentage, 47, 39, 60, and 70 percentage respectively. The moment you add fly ash, it was 27. The moment you go for the nanoparticles, it is increased to 60 to 70 percentage. So that is the advantage actually the moment you go for the nanoscale materials. So that is the way significant effect of SCMs on the chemistry or electric conductivity of pore solution depending on the alkali content, replacement level and age. So that is significant effect of SCMs on the chemistry or here we will say the electrical conductivity. Okay. Yes. Then let us see the setting times. Setting times is very important, like interesting picture here in the setting time. You can see here like this picture is, this histograms are my initial setting times and this line is my final setting times. Now try to observe actually. For a control, the initial setting time was 118 meter. The moment I have replaced 25% fly ash, you can see the initial setting time is increasing by 42 minutes. 42 minutes. And we know that is natural actually. The moment you add fly ash, your setting time, the hydration process goes slow actually. And that we know very well. But try to see, you keep on minimizing the moment keep on increase in the moment I go with the secondary cement materials, the setting time increased. But the moment I added nanoparticles, now in these last two mixes, their setting time was very similar to the control. Means even there are some results we have done actually, some research we have done where we have replaced like cement with only nanoparticles. Now these two, remember these two are combination of secondary cementitious materials and nanoparticles. So here replacement is 25% replacement. That is written as 25p actually. So out of 25, there are 2% on nanoparticles and 23% is your secondary cementitious materials. Now we have done some research. I will tell you, we have not plotted here. I have not plotted here actually. So if you are replacing only nanoparticles, there is a significant reduction in the setting time because of the faster hydration reactions. And if you are going with only nanoparticles, remember it is very difficult for you, for the mason to work with the material because it will not give much time. So initial setting time is reducing drastically. But here you see how it is beautiful. It is similar to the control. That is my advantage actually. So similar way here, the final setting time also in a similar manner, okay, the trend is similar in for the final setting time. So, so basically, okay, whatever I spoke here, okay, just a little here, the binary banded flyers is nothing but attributed to the slower initial positronic reaction of flyers particles. But the moment I'm going with the nanosilica encoded with flyers and ultrafine flyers mix, that is FNUN accelerated the setting time compared to other band mixes. So basically, what is the accelerating time? Reduction in the Raman period, faster rate of positronic reactivity, and hydration by nanosilica. So that is helping me, okay, when I'm adding the nanoparticles into the cementitious composite. Then let us see the surface temperature also. This is a very also important, very interesting actually results. Now you can see here the time versus surface temperature. Now surface temperature was measured through a infrared gun actually. Now you can see here, now this is my nanoparticle mix. This is my nanoparticle mix actually. The black one is nothing but your control, and the red one is your fly ash 25%. So it is natural, like the moment you add the fly ash, it is reducing the hydration reaction. So that is the way it is helping me. Okay, one in one other way I can say, when I'm going for a mass constructions, that's why I am going with the replacing the fly ash or the low heat Portland cement actually, and that is the way it is helping me in shrinkage prevention of the mass concrete. But let us see here now. The fly ash, the control temperature was 32 degrees centigrade. Remember, fly ash, ultrafine fly ash, okay, this significantly reduced actually. Unless the moment you go with the nanoparticles, it is okay. It's coming close to the control, but it is good. The good thing here is my okay mixes is not having much okay higher values as compared to the control actually. So it is almost okay similar okay range getting the control. Okay. Now same thing for the workability. So workability you can see here. So the advantage of secondary cementous materials is it gives me more workability. Okay, more workability. But the moment I am going with the nanoscale level, nanoparticles level, remember you are adding a material which is having more surface area. So more surface area means the water requirement is going to be more, and thereby your workability will be reduced. So that is the ideal. So, but here because the nanoparticle percentage is very less actually, so I am getting almost a similar level, slightly lower, okay, but similar level to the control. So there is no problem for me in dealing with the workability. Now come to the chemical shrinkage. Now chemical shrinkage values, that is milliliter per 100 gram. That is the way, okay, is the expression, okay. Normally we express and in the with respect to age. Now you can see here, same, okay, the shrinkage for a fly ash mix is the lowest here actually. For a fly ash mix the lowest. Whereas for a nanoparticle mix it's the highest. As I was telling you, this is the one of the disadvantages. The moment you go for a addition of nanoparticles, your shrinkage is going to be more. Now, see here in one of the mix, like that is, this is the last, okay, the topmost mix, that is UN25, that is ultrafine fly ash nanoparticle mix. After 14 days, you can see there is no results are being reported. Means the the test could not be done. The beaker, okay, where okay, the chemical shrinkage measurement was being done, got broken actually. Got broken because of the faster reactivity, okay, faster reactivity and higher rate of chemical shrinkage. Now I will show you the picture actually. We call this phenomena is the self-desiccation, which leads to cracking and even failure of the flux. You can see here These are the flasks were kept for the chemical sinkage measurement for all the mixes. Now, now you can see, okay, after 14 days, in one of the beaker containing nanoparticles got broken actually. You can see, okay, there is a larger cracks happened, okay. So that is the, so what you have to do actually? Well, so the point here is we have to have a adequate quality control practices. Your curing level should be absolutely proper, okay, when you deal with the nanosilica. Otherwise, you cannot avoid the shrinkage. So to avoid shrinkage, it is necessary to go for a adequate quality control practices. So nothing but we have to give more focus on the curing of the concrete or curing of the cementitious composite. Okay, now let us move into the thermogravimetric analysis. Now, how, see, as I was telling you, how to determine the hydration products is the very much key actually. Now, when you go to the TGA, now you see, okay, like normally, okay, I will explain you, then I will come to this one actually. So normally for a this is called TG, that is thermogravimetric and differential thermogravimetric plot. So the so this one actually, this one, okay, from you can see the blue one, so the green one is going, okay, top to bottom is nothing but my TG, that is thermogravimetric plot. So that is plotted in the this side of the left side of the y-axis, and DTG, that is differential thermogravimetric, is plotted in the y-axis, in the right side of the y-axis, and this is my temperature. And I want to tell you now why DTG actually. Now the moment you go for differential, okay, plot for this kind of curves, you will get a peak actually, and that peak will give me a identification of what hydration products at what stage, okay, of the test. So you can see here, now there is a peak, okay, prominent peak here, and I am sure, okay, this peak is nothing but my calcium silicate hydrate, or we say is the dehydration of water molecules associated to calcium silicate hydrate. So that is the my peak actually. Now the moment you come to the this one, this peak, this is nothing but my dehydroxylation of calcium hydroxide, and the last peak is the calcium carbonate, and that comes within the range of 600 degrees centigrade to 800 centigrade. That is decarbonation of calcium carbonate. But in this, okay, presentation, we have not, okay, calculated the decarbonation of calcium carbonate. But I will show you the determination of calcium hydroxide and calcium silicate hydrate. So as I was telling you, by adopting the equations, okay, that I discussed, okay, in the methodology section, if you adopt those equations, then you can determine the percentage of calcium hydroxide and percentage of doublets, that is water related to uh, the hydration products except the calcium hydroxide. Now you can see here. Now what is the peculiar, okay, like histograms here. Now this is my control motor, control pest, I would say control pest, and here it is my nanoparticle, okay, admixed pest, and these are my secondary cementitious material, that is fly ash and ultrafine fly ash mix. now now try to understand actually. Now this is, okay, presentation of 7 days and 28 days. So 28 days, so for a control motor, the percentage of CH was 19.98 percentage. Okay, now how much it was for a fly ash, only fly ash base mix, for 16.06 percentage. Now let us come to the nanoparticle, okay, admixed. Now that is fly ash nanoparticles. Now it is reducing to 10.62 percentage at the age of 28 days. So means you are reducing the percentage of calcium hydroxide. Well, what is the consequence? The reduction of calcium hydroxide is nothing but the reduction of the your permeable porosity and the improvement of the durability. Okay, so that is imagine, okay, like suppose as compared to control, the moment I proportion the mix with the nanoparticles and with the secondary cementitious materials, I am getting almost a half the porosity actually, half of the calcium hydroxide is getting consumed actually. So again, okay, now come to the right side picture. So this is just like a validation picture actually. Now here you can see the percentage of hydrated water that is associated to calcium silicate hydrates. So we know the more the calcium silicate hydrate is better for us actually, better for us. But for whereas the CH, less CH is better for us. So this is just a validation actually. We just calculate the calcium hydrate. You can see here with the it's compared to control, the nanoparticle admixed, the best is having much higher double H percentage. So that is nothing but your is, is consumption of calcium hydroxide and converting to the additional calcium silicate hydrate. Okay. And let us go to the the mineralogical composition. Like this is they're done okay through the XRD and and you can see now how we compare actually through the peak identification. Like there are okay like calcium hydroxide, calcite, baterite, quartz, calcium silicate hydrate, SiO2, calcium silicate. So these are the peaks. If you use high expert high okay like software, okay, then you can determine okay and give the name okay what are the peaks for actually. Now, now this is my control, like this is my control paste. You can see I'm getting some peaks. The moment I'm adding the secondary cementitious materials, then okay, slide to the nanoparticles, you can see how okay my peaks are getting intense. My peaks are getting intense actually. And you can see the more and more peaks are available for the calcium silicate hydrate, the quartz, the calcite, the vetrite. So there are the intensity is increasing actually. So that signifies the more hydration is happening within the cementitious system. Okay. So most prominent peaks like that is calcium hydrate found to be in the form of tobermorite and calcium hydroxide in the form of portlandite. So that is the way you can do okay. You can determine or you can categorize the peaks through the expert okay high software actually. So whatever I spoke actually I mentioned it here okay. Again no need to read. And last is the microstructure analysis to the SEM index analysis. Now you can see here these are my secondary electron mode images and these are my just morphology actually. You can but what it gives actually morphology will give you just okay how much my mix is getting dense. Now this is my control, this is my fly ash, again ultrafine fly is ultrafine, and these two are nanoparticles. So you can see here by seeing the picture you can see the pictures are getting looking okay more and more denser. But really with these pictures you cannot quantify or you cannot differentiate significantly. So that is the reason we go with the energy dispersive X-ray spectroscopy analysis. Now, now let us see what it gives. The moment you do the EDX analysis, now you can see here right side, it gives me a elemental peaks. Elemental peaks. Now, which are the elements are important for me? For cement is composite is the calcium and silica. So most of the cases, the atomic ratio of say SI, if you calculate, you can understand what level, okay, comparatively one cement mix to other cement mix is difference. So lower value of CA by S ratio, remember, characterizes the compact and densified microstructure of cement matrix due to the development of stronger network of CSS by means of CS consumption. So the moment CS is going to be consumed, so means the CS is consumed, okay, and making reaction with the additional element of silica and forms calcium silicate hydrate. Remember, so more CS is consumed means your CA value is going to be lesser actually. So CA by SI ratio is going to be less. So that will signify a compact and dense microstructure. So let us see what okay CA by SI ratio for all the mixes talks about. Now you can see here for a control CA by SI ratio for 7 days 3.06, and for a ternary blend, okay, nanoparticle is 1.925. Even for a binary blend, it was a hard 2.9 actually. And 28 days, almost half, because it is 2, okay, 2.18, and the moment you go here, it is comes to around 1.3, okay, it means most of the calcium hydroxide is consumed, okay, and that we say is nothing but your reactivity, the pozzolanic reactivity. So here I mentioned here the reduction of CFS ratio is due to the accelerated reactivity of nanosilica and the additional formation of calcium silicate hydrate. Okay. So with this, I can now move into the conclusion. So implementing the theory of particle packing, that is modified Anderson and Anderson model, the right proportion of filler admixtures could be proportions for the production of multi-blended cement paste and mortar. Then early age properties like setting time, surface temperature, flow properties were tailored with the combination of micron size, secondary cementitious materials, and nanosilica. And from TGA, the presence of supplementary cement material nanosilica combination showed the potential reduction in the calcium hydroxide amount and improvement in the doublage quantity. so, so with this, we can understand the ternary blended cement or ternary blended cementitious mix had an immense effect in the calcium silicate hydroxide and CS peak, but the additional CS peaks are much stronger after 28 days. And CA by S ratio is showing for ternary blended nanosilica admix samples at all ages, indicating a denser formation of calcium silicate hydroxide. Okay, so that is the way, like you can understand a sustainable mix can be designed even with a very small proportion of nanosilica particles. You no need to completely replace the secondary cementitious materials. You adapt secondary cementitious materials in a large scale, but by adding a very small percentage of nanoparticles, you can really develop a sustainable cementitious composite. And that is what is the key here in my presentation. So, so these are the publications. Well, there are so many publications has come up. I didn't update actually, but once you go to the my website, you can see. So the student, okay, the PhD student, okay, is Snehal, okay, she has published extensively, okay. Still, okay, there are another 3 papers actually she has published in very much reputed journals. And you can anyone of you who is working on this area can definitely refer these papers actually. And these papers also talks about the quaternary blended mix, which I didn't talk about. Even okay, there is another material called phase change materials also. So you can go through it, and if you have any doubts, you can really discuss with me. So with this, I am just closing my presentation, and thank you one and all. Thank you, Dr. Momin, for inviting me, okay, for this 5 days FDP program. So with this, so I will say, like, we shape our buildings, thereafter building shape us. That's what's given by Winston Churchill. So please, guys, so try to look into the quality, and that is going to define the next generation durability of the structures. So thank you one and all. Okay, so if you want, okay, like to discuss some more about some questions you are having, I will happy to answer.
Thank you, sir. Thank you so much for joining us and giving an introduction about the microstructure of a concrete and its characteristics by using nanotechnology.
Thank
Thank
you,
you
thank
so
you.
much,
Yeah.
sir. S- Now I ask participants, if you have any doubt, you can unmute yourself and ask the question, or you can even type in the text box, chat box. Any participants? If you have any question, please you can ask the sir.
I guess there are some text messages are there.
Yes, sir. Yes, sir. There is a one from Lakshmi Narayan Oja. Ma'am is
Okay.
asking that SCM, secondary or supplementary cementitious material. SCM means what actually SCM means, ma'am is asking.
Okay, 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 okay. Yeah. So SEM is nothing but okay, yes, as you Dr. Momin has told, okay, it is secondary cementitious materials or supplementary cementitious materials. I think
I think, yes,
I- yeah, I see participants. Okay, normally remain shy. Okay, in most of the presentations, and this is a little bit advanced. Okay, like topic actually.
yes.
So I don't mind. Okay, there is no problem. But anytime you feel like okay discussing with me, you really okay can like means send an email okay to this email ID. So I'm very much active okay in this email ID particularly. So you can revert me back. You can connect me actually to this email ID anytime, and I will happy to answer you actually.
Sir, there is one more question from
Yeah,
Dr. A. Patil.
yeah.
Ma'am is asking that for performing XRD, what care should be taken?
Well, there is no such care actually. Okay, like particularly I told you for a cementitious material, the biggest challenge is the stopping the hydration actually. Like like for example, your sample is like suppose 28 today is 28 days. For example, okay, I will tell you now. Today you may not get a slot okay for XRD. All right. So only care for us is the preserving the sample means stopping the hydration process. So that you can do to the solvent replacement techniques. And once you do this, okay, you can refer okay some of my papers which are listed here. There we have mentioned okay clearly what is a solvent replacement techniques, and if you stop the hydration process, so that is the 28 day, then that sample will represent 28 days anytime you put test. But and and XRD person, okay, the XRD operator will tell you okay like what kind of sample okay like he wants. Normally okay like it should be a powder sample. You have to grind it, okay, pass through a 75 micron and give it to the XRD operator. So other than that, there is no such okay care is required for doing XRD. Because remember, okay, this XRD we have not done by ourselves. The XRD test is being done in our central research facility. We don't have I don't in my lab I don't have a XRD okay X-ray diffraction machine actually. It is very costly. It is in crores. Okay.
Sir, there is one more question from Dr.
Yes.
N. Arunachalam.
Yeah.
Uh, Is there any special software or reference books for identifying the peaks obtained in XRD analysis?
Yes. Yes. It is. See, you have to go. You have to adapt the expert software. Okay, expert high score software. So that is the software I mentioned here. Some of the, I guess, remember slides. I remember. So I will go through the slides. So that is expert high score software. Okay. So the moment you go to that use the software, and it will give you the now that software you have to purchase actually. Okay, your institute has to purchase. Okay, and yeah. So here you can see I mentioned here the software is expert high score plus software. Now, if you use this software, the XRD machine will give you the only the diffractograms, like only the peaks actually, only the peaks. And the moment you upload these diffractograms in this software, and it is a software where the database okay of all the minerals already inbuilt, and it is very easy actually, and it will give you within no time what are the peaks corresponds to. Well, in our time, I will tell you, it used to take okay, 1 2 days. We used to go to the library, used to refer the books, okay, like refer the database, JCPDS, that's is it called JCPDS, okay, like it used to take 2 3 days. But now it is very easy actually. You just okay adapt the software and you can get the intensity, the peaks corresponds to which mineral. Okay, is it clear?
Yes, sir. Thank you, sir. There is one more question
Yes, yes,
from
please.
Lakshmi Narayan Oja. What are the
Yeah,
possibilities of for nano concrete in practice?
yeah, that is a very good question actually. Well, as I told you, like right now, okay, nano concrete is not being till now adopted it for the by the construction industries. One thing is because of its high cost. Well, we know how to maintain the adequate quality control. There is no problem for us actually. We can maintain it. But the
Feedback.
biggest challenge, particularly for a developing country like India, even many parts of the world also, even it is a very costly material. Like you are okay, like suppose per meter cube concrete you are getting from ready mix like plant is 4 to 5,000. Now this will increase to 7 to 8,000 actually per meter cube. That is the biggest challenge actually for us. Till now, nanotechnology is not being adopted okay wide scale in the construction industry. But remember, with the climate change, okay, with a severe climate change and with the global warming situation, now we are moving towards more and more sustainable material, more and more durable material actually. Now the point is the moment you go for the a durable material, now right now okay, like whatever the material we are adapting is a big challenge for the service life. So my point is why okay this research is required, because we have to develop more and more material, more and more sustainable material which will give me a bigger service life. Okay, and we should develop materials which will give us a new generation, okay, new generation idea which will sustain for the entire service life. That is very important actually. So okay, now the idea is at this point the construction industry is not adopting because of the high cost. Even the customer is not adopting because of the high cost. But with time, there will be change. We know, okay, the research that we do now may not be implemented at this point, but it will be definitely implemented okay, after some time. So with this, there are a lot of research is ongoing on the nanoscale materials, on the nanotechnology actually. So at this point, I will tell you, even in the Indian condition, we are not having okay a single application of nanoparticle except for ultra high performance concrete. So you know, India being a developing country, application of ultra high performance concrete is usage is very low actually. Is almost negligible actually. So, but the same kind of material like ultra high performance concrete is being used by developed countries. If you go to North America, there is okay a wide scale application of ultra high performance concrete. Okay, is it fine?
Yes, sir. Thank you, sir.
Thank you so much. Yes.
Thank you, sir. Thank you for sharing your knowledge. Now, I would like to ask our Vice
Thank you, Dr.
Principal,
Moment. Yeah.
Madam, to present a letter of appreciation.
Okay.
Ma'am, yeah, you can.
Okay. Uh, Very good morning to all of you. On behalf of our principal, Dr. Atul Aire, management, Faculty of Civil Engineering, and all the faculty of BLD Engineering College, I would like to thank Dr. B.B. Das, Associate Professor and GYAN Coordinator, NITK Suratkal. Sir, you gave a wonderful talk on hydration and microstructure properties of nanosilicon. Thank you so much, sir. You addressed the questions also, even though the questions were very few. Thank you very much, sir. And I just came to know that just through communication through a mail, you accepted for this session. That is how the people of high this one will be. That's what I think. Thank you so much for sharing your knowledge, sir. Please accept this certificate of appreciation from on behalf of BLDCT, sir. Thank you once again.
Thank you.
Sir.
Thank
Yes.
you. Thank you. Thank you, madam.
Yes.
Thank you so much.
Thank you. Yes.
Thank you, Dr. Momin, and thank you, one and all. Thank you so much.
Thank you, sir. Thank you.
Thank you.
We have another session on from Bibi Dibhushan Das also tomorrow again.
Yeah.
We'll again join, sir.
Definitely. Yes. Yes. Tomorrow, same
Definitely,
time,
sir.
we will join. Yes. Yes. Okay. Thank you.
As per the schedule. Thank you.
Thank you. Yes. Yes.
Thank you. Thank you. Thank
Bye.
you.
Have a good day, all of you. Bye.
Good day, sir.
Yeah.
Thank you, sir. Thank you. Next session
Thank you.
will start at 3 p.m. today. The session will be conducted by Dr. Mohammad Ashraf Iqbal, professor from IIT Roorkee. The topic is on behavior of pre-stress concrete under the impact loading. Please join us again at 3 p.m. Okay. Thank you. Thank you so much.
If feedback link is been
And
shared to
even
you.
feedback link is shared in the chat box. Kindly provide the feedback.
The next participant, speaker is from IIT Roorkee. I request all the participants to join early. Because today the speaker from NIT Suratkal joined at 10:30. Still, we didn't started. That is the goodness of our IITs and NITs. So I want all the faculties to join early so that the session may be started as early as possible.